Hello everyone, welcome back. In this particular video, we're going to talk about the Friedel-Crafts acylation reaction. This reaction is similar to the Friedel-Crafts alkylation reaction, but the outcome is different, and we use a different reagent here to get to that outcome. So this reaction installs an acyl group on an aromatic compound. So the reaction is achieved by reacting an aromatic compound. Example, benzene is the example that we are using here. So the benzene ring, when it's reacted with an acyl chloride and you use aluminum trichloride as the catalyst, the product that you get is a ketone. And if you look at it, what we're doing here is we are installing this acyl group, okay, on our products. So that's the acyl group. So we've added that carbon-containing group to the aromatic compound. Now, because this involves the acyl chloride and the alkyl trichloride, now, because this involves the acyl chloride and the aluminum trichloride as a catalyst, the mechanism of the formation of the electrophile here is something similar. So what happens is the acyl chloride reacts with the aluminum trichloride, and it gives rise to an intermediate. And this intermediate is going to have a formal positive charge on the chlorine and a formal negative charge on the aluminum. And from this intermediate, the bond between the acyl carbon and the chlorine breaks open and it goes to the aluminum such that we are going to get this carbocation. This carbocation is called the acyl cation, or it is also called the acylium ion. So this is the electrophile in our reaction now. Now, along with that, you also get the aluminum species, where the aluminum is a formal negative. This acylium ion is resonance stabilized because you can use one of those lone pairs and bring it down to form a triple bond. So you can bring that down, and that's going to give us a molecule where we have a triple bond. The oxygen has one lone pair and one formal charge. So the positive charge is not on the carbon then, but it's on the oxygen. So there is resonance possible in this particular case. But once this acyl cation is generated, the mechanism, the rest of the mechanism is the same. So benzene ring or any other aromatic can serve as the nucleophile, and it can attack this acyl carbon. So the bond forms between the benzene ring and the acyl carbon. So the pi bond attacks the acyl carbon. And this would give us the sigma complex, which is our intermediate. And as always, this sigma complex is resonance stabilized. We will not show the resonance this time, but it is resonance stabilized. And once the sigma complex is formed, it can react, or any weak base which is in the system can help deprotonate this hydrogen. And whenever we are working with this aluminum trichloride catalyst, it's usually the halogen on that. It removes, deprotonates, and it is going to install the acyl group there, plus HCl plus AlCl3. So that's how we get our ketone product in this particular reaction. So overall, aromatic compounds can react with any acyl chloride or any acyl containing species in presence of a catalyst to give you the product. So let's look at an example. So let's say if I react benzene with acetyl chloride in presence of aluminum trichloride, then the product that I get is going to be that. So the acyl carbon here is connected to the benzene. Along with that, we will get HCl and we will have aluminum trichloride, which are our byproducts. Now, the advantage to this reaction is that once we make this acylated product or the ketone that is made, the acyl group deactivates the benzene ring. Okay, deactivates means that it is going to slow down further electrophilic aromatic substitution. Okay, so the acyl group deactivates the ring towards further electrophilic aromatic substitution. So because of that, in case of the Friedel-Crafts acylation, we do not observe polyacylation because that process is going to be slower, because once you've installed one acyl group, it is going to slow down the addition of further acyl groups. So you will not see, or you can prevent the polyacylation from happening because it is going to be a much slower process here. So apart from avoiding the polyacylation, which is possible, there are other advantages to doing the Friedel-Crafts acylation reaction, because the product that we've made here, which is a ketone, this can be reduced. You can reduce it using, let's say, zinc and HCl under acidic conditions to make an alkyl group. In this particular case, it's just an R group here. So this is the Clemencen reduction. So that's the Clemencen reduction. So it converts the keto carbon into a CH2 here. So you get that. So you can actually convert your ketone into an alkyl benzene later. Why would that be an advantage? Because think about Friedel-Crafts alkylation. Primary alkyl halides do not participate efficiently in this reaction. But the Friedel-Crafts acylation could serve a solution to this purpose. So let's say if I want to make an alkylated benzene where there are 4 carbons on the benzene ring, 1, 2, 3, 4. And from the way this alkyl group is connected to the benzene ring, I see that the alpha carbon here is a primary carbon because that carbon would have been connected to the alkyl halide. So I would be unable to make it using a Friedel-Crafts alkylation, because if I took this reaction and took benzene, and if I reacted it with butyl chloride, so 1, 2, 3, 4, and with aluminum trichloride, this reaction may not be very efficient. Okay, this is not an efficient reaction to give us that product. But what I can do is I can take benzene and do acylation on it instead. So since I need 4 carbons, I will use an acyl chloride which has 4 carbons in it. 1, 2, 3, 4. And this reaction is going to work, and it would give us the acylated compound or the ketone product. So we get the ketone here. And once this ketone is made, we can do a Clemencen reduction on it and convert it into the alkylated compound. In the first example, it wouldn't work because the primary alkyl halide would not be able to generate the carbocation efficiently because primary carbocations are not that stable. So the Friedel-Crafts acylation reaction can be used to overcome some of the limitations that we encounter in the Friedel-Crafts alkylation reaction. So that's one advantage to the Friedel-Crafts acylation reaction. So I hope you find the discussion and the examples helpful. Bye.